experiment we'll do today is over another experiment of acceleration. This one is letting a ball roll down an inclined plane. It calls for 10 meters, but the driveway, since we're using that today, isn't quite 10 meters. So from this point, measured, here's our 2-meter line. You're looking at that upside down. 4 meter, 6 meters, and then down to 8 meters. We're going to do, let it roll, just let it go and let it roll down twice. We'll take the time twice. That's how long it gets down to 2 meters. Average that. We'll start back at the top and let it roll down to the 4 meter twice. Time that each time. Average it. Same thing with 6 meters and 8 meters. And then I'll explain another part of the video how to use this to calculate the acceleration. And we want this long, drawn out inclined plane to do this, since reflexes are a little slow, about 0.5, half a second longer to get the time than it probably would actually if we were using a photogate or something. We're just eyeballing this one. Okay, so we're going to be talking about Acceleration Lab. This is taken from Integrating High School Science by the Charles A. Dana Center at the University of Texas at Austin. The easiest thing for me though is just a little PowerPoint to help with this. Sorry about my hand shaking. Materials we need: a large ball. The original one said call for a bowling ball, but they're a little hard to come by. And we just used a basketball. Stopwatches, masking tape or chalk. Since most of the things are cement, like we used just a sloping driveway to do ours in, and we just marked off used the chalk. But depending on where you're at and what you're doing, you might need to use the masking tape. Measuring tape or a ruler with metric, that are measure it in feet and inches and convert it to metric. And the Acceleration Lab questions. Background. Actually, I'll just leave this on here and let y'all read this. And of course, that velocity, that formula there is velocity equals delta d, which means, that's the Greek letter in science. It means change. So change in distance divided by the change of time. In this case, it's the final distance minus the initial distance divided by the final time minus the initial time. That can sense a little bit of a run on there, isn't it? It will be assumed. It will be assumed for this investigation that the average speed and instantaneous speed are the same at the middle of the time interval. since our reflexes are slow, we're doing this over a longer distance and a slope that's 45 degrees or less, so that the ball's not rolling quite so fast that we can't hit the timer. You know, fairly close. Here's an example data table. Of course, depending on the slope of your ramp, this can change, and I'm not sure where they generated these numbers. If they were following their own directions, this, I'm not sure what the slope was, but they were probably using a bowling ball. So I think it'd be a little hard to, if the bowling ball really got it going fast at the end of the ramp, I'm not sure how easy it'd be to stop it if it's going really fast, so, or how safe that would be for depends on your students and the method they use to stop it, I guess. And just pause if you need to, of course, to read this. And we only got to 8 meters because our driveway wasn't long enough, so we only did it to 8 meters. And since I only have 2 students at the moment, my daughters, one of them would stop the ball, so we'd start at 2 meters. We did like 3 trials from 0 to 2 meters. They moved down to the 4-meter line, and then, and I would start the ball from the 0 and let it roll down, and then the recorded time it took from 0 to 4 meters. And then use the time, later on in the data table. We would just subtract the average time for the 2 meters from the time for the 4 meters to get how many seconds it took to go from 2 meters to 4 meters on average. Sample data time, it calls for twice, but we did 3 times for each one. So of course at 0 meters you got 0 seconds all the way across. And 0 to 2. And 0 to 4, and 0 to 6, and 0 to, how much time. And to get the time between one interval, later on you'll subtract the time for the average time for 2 meters, or from the time for 4 meters. Or is it vice versa? Find the difference.
See if we can get this focused. Okay. The acceleration lab questions. Describe the slope of your graph. What does it tell you about the ball speed? This is referencing the initial graph that you're going to create on your own. I said the original one called for twice. We went and actually did our experiment. The balls rolled down the slope 3 times, and then average of 3 instead of just 2. And then did graph it. We'll go over the results and things in a second video. 2, as the ball rolled down the ramp, its speed changed. Find the average speed for the ball for each 2-meter interval. Record your answers in the data table provided. And I'll try to get copies down in the link below of these questions so you can copy and paste, or you can just pause and type them out. Of course, you can make this on yourself. What happened to the speed of the ball as it rolls down the ramp? What word do scientists use to describe it speeding up? And this is for high school level. Question 4. Acceleration can be calculated using the formula A for acceleration equals change in velocity divided by change in time. That will be written as final velocity minus initial velocity divided by the final time minus the initial time. What was the ball's acceleration between 0 meters and 10 meters? In our case, it was 0 meters and 8 meters. Use the end time at 10 meters for a change in time. If the ramp continued for another 10 meters, what would happen to the ball speed? Estimate the ball speed at 20 meters. So this calls on them to analyze the data they have and extrapolate from that. Extend what if the pattern continued to predict an outcome. If the pattern continued as it is, that's what they observed. Question 6: acceleration expressed in meters per second squared or meters per second, which means that acceleration tells you how much an object's speed will change each second. Based on this idea, what is the ball speed after 1 second? After 2 seconds, after 10 seconds, after 30 seconds. Again, this gives them a formula and shows how once we have these formulas and these observations, we can actually predict probable outcomes based on these patterns. Question 7. A 2004 Saleen S7 can accelerate from 0 meters per hour, or miles per hour, or 0 meters per second, to 60 miles per hour, which is 26.8 meters per second, in 2.9 seconds. So we did the metric. It would take a Chevrolet Corvette 4.2 seconds to do the same thing. Find the acceleration of both cars in meters per second squared. Note, the Saleen costs $395,000. The Corvette sells around $50,000. Now, does that have anything to do with the problem? No. And of course, in standardized tests, things like that, which we do a lot in Texas and the rest of the United States, that's just a distractor. You have to learn to say, does that have anything to do with what they're asking me? No. Question 8. How fast would each car be traveling after 10 seconds? And question 9, about how long would it take each of these cars to reach 100 miles per hour, or 44.7 meters per second? course, this is synthesis. They do an experiment, they see how the patterns are used to predict outcomes or probable outcomes, and then they go on to apply this to some of these hypothetical situations here, scenarios. And last question. If you enjoyed this so far, I want to go over the answer to this in a separate video. If you enjoy the video, please hit the like button, hit the subscribe button, and hopefully these are improvements on my past few, and they'll continue to improve as we go along. Thank you for your time and your attention.